So as some of you may be aware, we have telescopes that are beyond Earth's orbit, telescopes that are orbiting the Earth. And why would we want to do that? Well, we don't put a telescope in orbit because we want that telescope to get a little bit closer to the stars. Because the distance that little bit closer it gets, it's insignificant. But the reason we do put telescopes beyond Earth's atmosphere is to basically avoid a few things. One of them is telescopes out there will not be distracted by light pollution. I mean, for instance, if you live in town and you look up at the nighttime sky and you try to make out some stars, well, the stray light from your surroundings basically kind of wash out the stars. Okay, you go out then on the same evening out into the middle of nowhere that has no stray lights, and you're going to see a lot more stars. So light pollution is an issue with just our naked eye, and it's an issue with telescopes. Another thing, and these both have to do with the Earth's atmosphere, is one thing about the Earth's atmosphere is it's not homogeneous. The Earth's atmosphere is not, well, there are pockets of cold air and warm air is the biggest thing. And they kind of do swirly things, that sort of thing, within the Earth's atmosphere. And if you're trying to look to gather photons from a distant object, this turbulence can really kind of play havoc with that process. And the other thing related to the Earth's atmosphere is it will literally block out some of those wavelengths of energies in the electromagnetic spectrum. So, and we're glad for actually this blocking effect. For instance, our atmosphere blocks incoming gamma rays and incoming X-rays that the sun and other celestial objects are emitting. But if you're trying to make a telescope to look at those wavelengths, you're kind of out of luck. So one telescope that we have orbiting the Earth, I think it's kind of in a pole-to-pole orbit, is the Hubble Space Telescope. And the Hubble Space Telescope has been up there for years now, and it has set us back some awesome pictures. It's about the size of a school bus, and it is a reflecting telescope, and it gathers light in the visible part of the electromagnetic spectrum, the Hubble Space Telescope. I mentioned light pollution, how stray light can make it difficult for us to discern images from objects. Okay, and so this is just kind of a composite image showing you where we have light pollution. Turbulence, I mentioned, actually is caused by, most notably, pockets of air at different temperatures that are kind of swishing around up there. What happens is that you know how light refracts, sorry, not light, I'm sorry, you know how glass or a lens will refract incoming light? Well, because it acts as a different medium. Well, if you have blobs of air, some blobs of air cold, some blobs of air hot, they actually act like two different mediums. And so we get this sort of kind of wavy sort of looking thing. And we call it twinkling. But notice that the angular resolution can really be affected. So this is a star viewed with a telescope that's on the Earth. And this is that same field of stars actually viewed from Hubble. Notice the angular resolution from the Hubble is a lot better. So the Earth's atmosphere absorbs most types of electromagnetic radiation. And this kind of shows you the different forms that are absorbed. So for instance, gamma rays are blocked. X-rays, are blocked. So actually, it's surprising we get much radiation that comes in. Okay. So just to kind of, we've been talking about telescopes in outer space or beyond Earth's orbit. Here is an assortment of telescopes, and just kind of their information with their starting dates down there at the bottom. And they are kind of, the way this figure is the telescope is lined up over the wavelength that it studies. So for instance, the Fermi and the Swift are looking at gamma rays, the Chandra is looking at X-rays, the Spitzer and the WMAP looking at longer wavelengths. Well, one of the things is that the light pollution issue, actually that's something that we here on Earth can fix. You know, we can maybe take our telescope and go out into the middle of nowhere, or we can work in our community. There are some lights that are more favorable, sensitive to people who are trying to use telescopes and view the nighttime sky. So we can work on that. And turbulence we can kind of work on. I'm going to show you a gizmo coming up here in a minute called adaptive optics, and that is a way to kind of get away from, to kind of correct for the Earth's turbulence. But one of the things we can't correct for here on Earth is the fact that the Earth's atmosphere basically absorbs certain forms of radiation that are trying to come, it just doesn't let that radiation come through. So this is an image of Chandra, who's looking in X-ray region, electromagnetic spectrum. So you can kind of see here is the little hole that it's collecting the light. I think that's right. And then over here would be the reflecting. Actually, X-rays they use, I think, a glancing technique. So it's not your typical reflecting telescope. But this little flap here, I'm pretty sure, and I could double check, but this little flap here I think is supposed to, when we have solar storms, it can close and protect the optics inside. All right, so adaptive optics, they help compensate for turbulence in the Earth's atmosphere. So that's something we can, that causes twinkling, we can fix that to a certain extent. So for instance, these are both images of the same region of sky. The first one is without adaptive optics, and the second one, can you see the resolution now using adaptive optics? So this would be a land-based telescope that is compensating for turbulence. And I'd have to double check, but what it does is kind of, it's segmented, as I understand it, and what adaptive optics does, it has some way senses the turbulence and then reshapes the mirror to correct for it. It's pretty darn cool. All right, again, left to right. The first one is without adaptive optics, and the one on the right is with adaptive optics. And this object is Neptune. These are both land-based telescopes, taken from land-based telescopes. From left to right. When we study the Jovian planets, beginning with Jupiter, Saturn, Uranus, and Neptune, we're going to see that they have their fair share of moons, and Io is one of Jupiter's moons. And so this, from left to right, is looking at Io without adaptive optics, and see how our resolution improves when we have adaptive optics. Interferometry, especially with the longer wavelengths, like radio waves, the wavelength is so long that in order to get decent angular resolution, we basically need to combine. We need to have combined signals. We need to have pieces of our telescope set far apart to go ahead and gather information and then recombine it into one image, and that's called interferometry. The very large array is shown here, and that's a famous one in New Mexico. So it's a network of radio telescopes that then pull their signal together to create a single image. And the last slide is how else could we avoid Earth's atmosphere? And the other is, well, why not put telescopes on the moon? It's a thought.